Talking about how to implement the star triangle in our NASM program, and this is for the Module 9 assignment. So first, just so we have a sort of outline, we're going to be running over the key components of how to run an actual NASM code, and we're going to be explaining the algorithm, and then we're going to show the implementation at the end. So jumping right into it, we begin with the section.data. And this directive basically shows us that this is where we would basically define our unchanging constants and variables. So for example, in C++, if we're to use the analogy of defining like a max number for an array, that's something that does not change. So we would probably use section.data for something like that. Section.bss, we did not need to use that for this program specifically, but normally for the more intermediate programming challenges using NASM, we're going to require this because this is where we define our actual variables that can be manipulated and changed throughout the program. So for example, have an accumulator in a C++ program where we keep adding to that accumulator. It would be defined in section.bss rather than section.data. And then section.text, this is basically where we begin our entire programs, is that this is what holds the bare bones and basically the meat of the actual program. So we would follow this by a global start, and then or whatever label we want. Instead of just the underscore start, we could write a number of things. But for the uses of this program, we just needed one basic main program, or a driver, so to speak, and then we would use that label for our driver, which is start, which is basically like main. And that's basically it for section.text. So jumping into our algorithm, as you can see here is a screenshot of the algorithm that I used. We begin with section.data. We haven't had any actual constants or variables that we needed to be defined. But section.text, we can see 4 messages, and they're in green. And then we can see a len underneath them, and I'll explain that now. So you can see message and then db. This is how we proceed our actual string, so to speak, or our message. And our string literal is going to be in quotation marks, much like in C++. And you can see there are spaces here, and that is done purposefully. We'll talk about why that's done. And we end our string literal with a quotation mark and then a comma, and then you see a 10. The 10 is one variation of how you can use a new line character. There are many others as well, but the easiest is just the 10. On the second line, following the message, you see len. And they're numbered according to 1 through 4. So the first len, you could see len1 equals, that's EQU, the dollar sign, so to speak, and then the dash, and then message 1. So basically what this is stating is this is the syntax for finding the length for your message and saying this is the length of it, basically. This is how many bytes it is. And that takes in consideration white spaces and things of that nature as well. And that basically is what you see going 1 through 4. But now going into why there are the spaces, we can actually start by looking at a pyramid. And a pyramid, you have a row on the bottom, and then it's centered. So we have the third to last row, or the row above the last row, being slightly less in its bricks, or you could say stars for this example, and then it just keeps going up until the last star is just 1 and it's in the center. If we were to remove the white spaces, it would not be centered. So to center it, our algorithm basically is we start at the bottom with however many stars we require. We go up a level, we do 1 or 2 less stars, we do a space. And then we do an additional space for the third one, and then an additional space beyond that in the last one. Or if you're looking at it from top to bottom, that would have been the first one. So basically, this allows us to center our pyramid or star triangle, so to speak. And it's a very simple algorithm, and it's even one of the beginning algorithms that's used for C++. So now looking at the implementation, it might look a little confusing because there aren't any spaces. I did that so that way the screenshot could kind of encapsulate the entire code and we could see it in the slide. So you see the global start, and then you see the start label there with the colon, and that's basically saying this is our main driver or program. So you see the move. We're basically moving message one into ECX, that's our register, and then we're moving the length of our message one into our EDX register. And another thing you'll notice is we're moving 1 into EBX and we're moving 4 into EAX. Now, this is basically our structure for printing or outputting a message. So if we were, for example, to read an input from the user and output that, we would use the 4 in register EAX and the 1 in register EBX, respectively, so that we can print something. And the ECX would be our message, and the EDX would be the length of that message. Because we hard-coded basically our pyramid, meaning we did not accept input from the user. We already predefined the length of it and the bytes and all of that. So that's why it's such an easy process to output. Otherwise, normally it would be a little bit longer. You would see a variation of 3s and 1s where we would take input. And now, lastly, you see the int OX80, and that is basically the end of our first message. It's basically allowing it to be processed and go through, much like a system exit or a return 0 or something like that. And then you see the same thing going on through messages 1 through 4. So then you see the same thing going on for message 2, message 3, message 4, until you get to the bottom where you see the end of code comment I made. And if I haven't already clarified this, the comments, much like in C++ where we use 2 backslashes, in NASM we use a semicolon. So going down to the comment where it says end of code, the last 2 lines of code you can see are move EAX1 and int OX80. Again, that's the same int OX80 we saw. That was at the end of all 4 of our messages, basically. And this is much like the actual system exit call that we would use in C++, but it is the system exit call that we use in NASM. So you can see a lot of parallels between the languages. So that is basically it for how to code and implement the triangle. And just summarizing and concluding what we've learned today, we've learned the structure of NASM. It begins with the section.data. That is basically where we define our constants and variables. Section.bss is the opposite of that, where we can define our variables that are allowed to be manipulated or changed throughout the driver. Section.text, this is basically showing us where we will see actual coding begin. And then from that, we see the global start, which is, for our case, where our main is going to be implemented, and then the actual label start, where you see the code for that. And then we end with the system exit. So it's very, very easy. It only has a few extra steps above C++. The algorithm itself now, what we learned from that was that it was pretty easy, much like a basic algorithm in C++ where we had to hard code pyramids and things like that. Basically, we start at the bottom with no spaces. We go up a row, or a row, and then we give an additional space. The one above that, an additional space beyond that, so that has 2. And then the one above that has 3 spaces. And then it just keeps going until you have your last digit or your last star or asterisk, and then you know that it is centered. And you can always run it and see if there's something that is not aligned, and you can always align it with a number of white spaces. So it is a very simple algorithm to implement. And going on to the implementation of the algorithm, we saw how we went about that. We saw the registers that we use in NASM, and we saw that if we were going to be printing, we would require the digits 4 and 1 respectively for outputting. Much like printing a line in Java or in C++, we would use cout. And it's just that simple. And we learned that, besides the 4 and the 1 for outputting, we also needed the message variable, which we would call message 1, message 2, message 3, message 4. And we would also need another variable for the length of those. Or if we were not creating a variable for the length, we could have just wrote how many bytes it was there. But just for the ease, we had an additional variable for the length. which correlated with its message, for example, message one, length one. And that was it. That was how we implemented our program. And then we ended at the end with the system exit. And it's really that easy. So that is it. And thank you for listening.